Hi, ladies and gentlemen. Welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today, what we're going to do is we're going to take a look at covalent bonding. Now, covalent bonds occur between two atoms when they share electrons to form a molecule or a polyatomic ion. And what we see is the electronegativity differences between the two atoms determine if the bond will be a polar or nonpolar covalent bond, and also determine the amount of ionic character present within that bond. Now, covalent bonding, and we'll take a look at it here, again occurs between two different atoms. And so I've just sketched on the screen the nucleus and the valence electron shell of two different atoms, right? And what we have to understand is that each nuclei is attracted to the adjacent atom's valence electrons. And so what we would see here is that the nucleus on the left is attracted to the valence shell electrons on the right, and that the nucleus on the right is attracted to the valence electron shell on the left, right? And we've seen this before. Electronegativity describes this attraction, and we understand up to this point that electronegativity is based on Coulomb's law, right, and the shell model of the atom, where if we were going to argue differences in electronegativity, we would be looking at, hey, where are my valence electrons located? What energy shell are they in? Are there any differences in shielding present? And then if all of those are the same, then what we would say is electronegativity would be determined by nuclear charge. So this is something, again, that we have seen before. But just to make sure that we're all in the same place, I've sketched a periodic table on the screen here. And remember, we've got metals versus nonmetals, and then I've got arrows on the screen indicating, right, as we move across a period from left to right, we understand and remember that electronegativity increases because Coulombic attraction increases, right? And then as we go up a group, right, those valence electron shells get closer to the nucleus, which also increases the Coulombic attraction, i.e. electronegativity also increases. But the thing that I want you to understand and kind of give you a guideline on here and take a look at is that my nonmetals have relatively high electronegativity values, right? If this represents the highest electronegativity area on the periodic table, then we understand that as we get closer to that point, electronegativity is going to increase. So nonmetals are relatively high electronegativity values. So now that we understand the sharing of these electrons is really determined by the electronegativity differences, we have to start looking at what are my ranges of these electronegativity differences. And so what we see here in this triangle here is just delta. It's just telling me to take a difference or subtract the two values, right? Is that when we have equal sharing of valence electrons between two atoms, we form what's called a non-polar electron cloud. Now remember, polarity is just an asymmetrical distribution of electrons, right? So it should make sense that if I have electronegativity values that are roughly the same, then electrons are not pulled to one side or the other of a particular bond. And so let's take a look at an example here. If I have a hydrogen bonded to a hydrogen, the electronegativity value of hydrogen is 2.2. And so if I look at this delta electronegativity value, it's actually going to be equal to 0. And so what we see here is that these shared electrons in this covalent bond cannot be pulled in either direction, and so they're equally shared. We get a symmetrical sharing or a symmetrical distribution of electrons between those hydrogens. Another example would be a carbon-hydrogen bond. Well, carbon has an electronegativity value of 2.6. Hydrogen, again, is 2.2. And so my change or my difference in electronegativity here is actually 0.4. Now, this becomes an arbitrary number, that 0.4, because carbon-hydrogen bonds are actually assumed to be nonpolar, right? And you've probably heard me say this before in class, is that all hydrocarbon chains are actually polar themselves. And so this becomes our demarc, is that some difference between 0 to 0.4 is actually going to be considered a nonpolar covalent bond. Even though we would expect a little bit of an unequal sharing of electrons here with carbon and hydrogen, it's not going to be enough for us to say and give it enough ionic character here to say that it's actually a polar bond. So 0 to 0.4 electronegativity difference is going to be a nonpolar bond, and it represents an equal sharing of those electrons. So now what we want to do is take a look at when my electronegativity values are actually greater than 0.4, we end up with a polar covalent bond, and the polarity is caused by that high electronegativity value element pulling the electrons towards itself, so we get that asymmetrical distribution of electrons. So what an example that I'll show you here is a carbon-fluorine bond. Well, we've seen the electronegativity value of carbon is 2.6. Fluorine is 4.0, and so my change or my difference in electronegativity here is actually 1.4. And so now we see that we're above that 0.4 value, and so what this is going to be called is a polar covalent bond, because since fluorine has a higher electronegativity value, it has a higher attraction for carbon's valence electrons, right? And it pulls those shared electrons towards itself, creating that polar bond. And so what I end up with is, we can look here, my carbon fluorine, we would diagnose it or draw it this way. And what this arrow, the easy way to remember this arrow is showing my dipole moment. It's showing which direction my electrons are actually shifted. And so what happens is, because electrons get shifted to one side of this bond, the carbon ends up being a partially positive and the fluorine ends up being a partially negative. And there's my dipole moment, right? And just remember with this arrow, if you don't get this into your head right now, it becomes confusing later. It always shows which direction the electrons are being pulled towards, and you can kind of see the positive built in to the back end of that, right? And so, but is this infinite? Can I have an infinitely large electronegativity value and it still be covalent? Well, the answer is no. So generally my polar covalent bond values are going to range between an electronegativity difference of 0.4 to 1.67. And so at that 1.67, it seems to be this magical point at where the ionic character of the bond actually becomes more prevalent, right? And we'd say that the bond becomes an ionic. So now what we want to do is we want to make sure that we understand what this ionic character is, because I keep actually referencing ionic character. Well, ionic character is exactly what it sounds like. It's how much does the bond behave like an ionic bond, right? And the understanding here is that all bonds have some ionic character. Well, we're not going to get too crazy with this. We have to understand we've got a set of values here so far, right? And we see our electronegativity differences, if these are labeled electronegativity differences, that 0 to 0.4 would be generally considered nonpolar covalent. 0.4 to 1.67 is considered to be polar covalent, and greater than 1.67 is considered to be ionic, right? But the only real way to understand what kind of bonding is present is really to examine the properties, the physical and the physical properties generally are the best way to determine the types of bondings that are present. But the fake it till you make it, or the really quick and dirty, we're still going to use our non-metal. Our non-metal is going to form a covalent bond, and our non-metal, I'll abbreviate there, is actually, we're going to assume, form an ionic compound. So we're not going to overthink this, but we're going to understand that ionic character is present in all compounds, and it's just how much is there. So we would assume the greater my electronegativity value becomes, so as I head that direction on the scale, my ionic character actually increases until it becomes what we would say completely ionic. All right, so now what we want to do is we want to take a really quick look at what's going on during these bond formations, right? And so I've got a graph on the screen here, and we'll kind of walk ourselves through it. And this is really what's occurring as far as energy and distance between the nuclei when our covalent bonds form. The little blue dots up top represent two hydrogen atoms, right? And we're going to progress through bond formation as these two hydrogen atoms approach each other. So we can see over here on the right side that there's very little interaction between the two hydrogen atoms when they're very, very spread apart, right? But as the two hydrogen atoms move together, what we see in this general area of the graph, right here, is as they approach each other, this ends up being an attractive force. Again, this is driven by my electronegativity values, right? Each nuclei becomes attracted to the adjacent elements' valence electrons, and they start to pull each other towards each other, right? And so I get an attractive force, and you'll notice as the attractive forces, as my nuclei approach each other, my potential energy is actually dropping, right? So it's a release of energy, which again drives home that statement, my bond formation represents a release of energy. It represents a low energy state for those two nuclei. So as the two nuclei approach each other, they're releasing this potential energy. They become and it's driven by the attractive force. We reach a point where they kind of balance, right? They get a distance between each other where attractive force is actually maximized. And then if they move any closer, we have to understand the opposite of attraction is actually repulsion. And so on the other side, when the nuclei get too close to each other, because they're positive nuclei, right? So positive repels another positive, that if we push them too close to each other, we actually get a net repulsive force. And so what we call this area that I've got denoted here, this is actually my bond length. And so we understand that certain bonds have certain bond lengths. And what that represents is the distance between these two atoms where my attractive force and my repulsive forces are actually balanced. And so it's important to understand, again, that bond length occurs when my attractive and repulsive forces between the two elements are actually balanced. And then the other thing to understand here, because we discussed as my atoms move closer to each other, it's a release of energy. And what we understand is that this area here, this actually represents your bond energy. And a big thing, a big idea, ladies and gents, is that the bond energy is the amount of energy that's needed to break a bond. And this becomes a very sticky point, because we just discussed, hey, this bond is being formed. It's a release of energy, right? So bond energy, the way that we describe it, is the amount of energy that I would have to put in to take my bond or my atoms from this point here where attractive and repulsive forces are balanced, and put them back over here where there's very little interaction. So bond energy is an input of energy. It's an endothermic process. Bond energy is an input of energy. It is an endothermic process. And normally your units of bond energy are kilojoules per mole. And again, the understanding here is you need to understand bond energy is the amount of energy needed to break a bond. We can look at this graph and determine bond energy, because how much, right? This is a scale on my x-axis of potential energy. How much energy would I need to take it from this point back up to this point where there's very little interaction between the elements themselves, right? So, and the other big thing to understand here is that notice as the bond's formed, right, as I'm going back this direction, it's that release of energy. So bond formation is a release of energy. It's exothermic. To break a bond, I have to put energy in. Very big idea, right? Make sure that you get your head wrapped around those two different things, right? The difference between how do I break a bond versus what's going on when a bond is actually formed. What's going on with the energy there? This graph will describe all of it, right? As the bond forms, it's releasing energy to break a bond, which is defined as bond energy. That's how much energy I have to put back in to take from my bond length back up to very little interaction. Well, all right, ladies and gents, that was quite a bit. I hope you have it all down. If you have any questions, I'll see you in tutorials. Otherwise, I will see you in class.